Good afternoon, everyone. My name is Wang Yin, and the topic of my presentation is MiniChecker, detecting data privacy risk of abusive permission request behavior in mini programs. In recent years, a new type of application known as mini programs has been gradually replacing traditional Android applications. These mini programs are highly convenient, lightweight, require no installation, and utilize web technologies while offering native capabilities. Their excellent user experience and low development costs have fueled their rapid growth, with the total market volume now surpassing that of Android applications on Google Play. Mini programs can perform functions traditionally handled by Android apps, such as shopping. For instance, when a user places an order on the Starbucks native app, the system prompts for location access. In the Alipay mini program, the super app, Alipay, requests permission to use location data. Both use a permission request mechanism that transitions from permission application to data acquisition. However, we have identified some issues with permission requests in mini programs. Let's look at a case study. In this case, a user opens the mini program. He clicks Mine, go to the login page, and decline the permission request pop-up. When he navigates back to the login page, via the cart page, a looping authorization issue arises. The user is forced to either agree to the authorization or close the mini program. This is a terrible experience. And more importantly, according to the GDPR, the controller shall take appropriate measures to provide any information and any communication relating to processing to the data subject in a concise, transparent, intelligible, and easily accessible form, using clear and plain language. This coercive behavior violates GDPR's requirements for openness, transparency, and voluntary consent. So how can we avoid this problem? We consider three key questions to understand the issue. How does it happen? Are there any other similar issues? And how can we detect them? First, we downloaded and decompiled the mini program source code. Our analysis revealed that these issues stem from a synchronous calling relationship. Each time a page reloads, the permission request API myGetAuth code is synchronously called by the page's onLaunch function. Next, by analyzing legal requirements and manually testing a batch of mini programs, we identified some permission-related issues. We categorized these into 5 types: home page pop-up, requests permission as soon as the user enters the app, overlaying pop-up, 2 permission request windows appear simultaneously, bothering pop-up, a permission request reappears during app use after being denied, repeating pop-up, similar permission requests continue after one is granted. Looping pop-up, users are trapped in a loop where they cannot deny permission requests until they agree or close the mini program. Finally, how to detect these issues. We consider 2 core strategies: constructing a call flow graph for key functions in mini programs and defining features to match different permission issues. Accurate detection is challenging. First, how can we universally identify the execution sequence associated with permission requests in a mini program? Mini programs often use predefined objects like app and page, frequent cross-file and cross-module function calls, and template relationships to introduce event functions, which traditional JavaScript call flow tools cannot analyze. Second, how can we recognize different abusive behaviors from the execution sequence? Different permission issues correspond to various triggers, states, and execution sequences, with program conditions and branches affecting risk assessment. Accurate classification requires a comprehensive consideration of these factors. To address these challenges, we developed MiniChecker. It first extracts a universal function call graph from the source code, then propagates behavior, and finally identifies the type of permission issue through feature definition and risk classification. In the first step, we use the general concept of a function call flow graph in program analysis. When a function declaration and its call are found in the program, they form an edge in the call flow graph. In mini programs, we focus on function declarations, function expressions, arrow function expressions, function calls, and method calls. We then supplement the analysis of broken function call flows in mini programs. For predefined objects, we supplement call relationships caused by this references and the global function getApp. For module functions, we supplement the module call relationship from export to import. Mini programs also frequently use anonymous module features, and we associate these indeterminate definitions and calls through textual matching of function names. For event functions, in addition to traditional event attribute bindings, we handle template files. Specifically, we analyze template statements to find cross-file event call relationships. In the second step, we propagate behavior on the call flow to determine the endpoint functions that ultimately call permission requests. We categorize endpoint functions into PLT and AET. As shown in the slide, the call chain on the left ultimately calls through app.onLaunch, meaning it is synchronously called with the lifecycle function and marked as PLT. The call chain on the right calls through page.event, meaning the permission request is only called when a user-triggered event occurs. This classification is used for feature matching. In the third step, we use a three-stage model to deconstruct the execution sequence into 3 steps. Pre-action, which is the condition stage that determines whether subsequent program behavior can be triggered. During action, which refers to the permission request pop-up and user interaction behavior. And post-action, which refers to the program's callback behavior after user actions. To determine the execution sequence, we consider the dominance relationship between calls, including PLT without branch conditions, AET after initialization functions, and user interaction behavior during page transitions. When these situations occur, we consider that when one behavior is triggered, the subsequent behavior will certainly be triggered. Finally, we define behavioral features to achieve final classification. We focus on the data type of permission requests, call locations, preconditions, and subsequent callbacks. Based on these attributes, we define features for each type of risk. For example, for homepage pop-ups, the feature is the existence of a permission call at the mini program's homepage. Finally, we present some examples. P represents different permission call APIs. As shown in the slide, a homepage pop-up occurs when P1 is associated with the startup function onLaunch, while a looping pop-up occurs when P6 loops to call itself. In the evaluation section, we address 3 research questions. Effectiveness. What is the effectiveness of our approach in detecting abusive issues? Improvement. How much improvement can our method achieve in risk detection compared to traditional JavaScript analysis tools? Distribution. To what extent are abusive issues prevalent in mini programs in large-scale real-world environments? First, we collected 54 risky mini programs and manually confirmed 128 risk behaviors. MiniChecker accurately detected 122 risk behaviors, with 26 false positives and 6 false negatives, achieving a precision of 82.4% and a recall of 95.3%. Further analysis revealed that false positives were mainly caused by dynamic conditions, such as status codes and network requests, affecting behavior triggers, while false negatives were mainly due to dynamically loaded libraries, such as complex encapsulation by the AntMove library, which renamed some permission request APIs, making it difficult to locate behaviors. Second, we compared MiniChecker with traditional JavaScript tools in detecting mini program risks. We found that TOJs could not correctly parse mini program source code. Approximate CG tools could not handle key-value function definitions and references commonly used in Mini programs, and CodeQL could not associate layout files, meaning it missed important event functions. MiniChecker effectively detected all risk types. Finally, we analyzed 20,000 real-world samples and identified that 30,866 Mini programs contained at least one risk issue. Among these risky Mini programs, each had the bothering pop-up issue. Among all permission request issues, API calls related to personal user information were the most frequent. Our research led to two findings. First, there are still some poor implementation mechanism designs in Mini programs, such as unclear API differentiation and synchronization issues between different APIs. Second, some developers lack privacy awareness, focusing more on convenience and neglecting privacy, such as preferring to loop and forcibly request user information. We propose two suggestions. First, add a Do Not Pop Up Again option for all APIs, and second, optimize API design. By distinguishing different API types for obtaining user information, to avoid repeatedly requesting the same information. The threats to the validity of MiniChecker include 3 points. First, complex dynamic branches can reduce detection accuracy. Second, it cannot handle obfuscated program code. And third, our analysis samples are primarily from one platform. We plan to continuously improve in future work. For example, for obfuscated code, we plan to collect some obfuscation cases, determine the obfuscation techniques used through classification methods, and attempt to restore the source code for risk detection. In conclusion, we identified 5 types of permission risk issues, found that existing tools could not accurately detect these issues, and designed MiniChecker to achieve accurate detection and uncover security issues in real-world samples. That concludes my presentation. Thank you.